All right, welcome back. So this is an ALEKS topic that's called percent yield of chemical reactions. But really this topic is a balancing chemical equations topic, it's a limiting reactants topic, it's a theoretical yield topic. It's all of those things sort of mixed into one question, which is really awesome. So let's go ahead and get into it. Anytime we're working on a problem like this in our stoichiometry section, this first step is always going to be to start with a balanced chemical reaction. If you do not do this, if you are not starting with a balanced chemical reaction or balanced chemical equation, basically like there's no way you can get it right? So like you're dooming yourself from the very beginning. So always we need to be starting with that balanced chemical reaction. So for these types of problems, if I see liquid octane written out CH3 CH2 I'm just going to rewrite that as something that's easier for me to deal with, easier for me to sort of visualize. C8H18. So just add up all of those. That's what I'm going to use when I write out my balanced chemical reaction. So C8H18 reacts with oxygen gas to form carbon dioxide. I guess I should be putting in my phase labels here. It's not really relevant for this problem, but it's a good practice. I'm just lazy, so I'm going to leave them off. So my balanced chemical reaction, so here I've got my different reagents and my products, but I haven't balanced it yet. So we always want to make sure that we're going to go through and balance this chemical reaction. So I'm just going to go ahead and put in the correct coefficients here. My strategy for balancing this probably would be to first deal with my hydrogens. So I would have 18 here and 2 here. So I would have thought initially to put a 9 here. But since I know that I need to have an even number of oxygens, I'm going to go ahead and double that right from the very beginning. So this will be 18, and then I'll go through and figure out, well, I need 2 of these to make sure that I've got 36 total hydrogens, and then 16 carbons because I've got 16 carbons here, and then add up my oxygens. I should have 50 oxygens on this side, so 25 O2s here. So, if you need more help on balancing chemical reactions, definitely there's other videos you can take a look at. But we need to be able to get to this point before we even finish reading the problem, right? We haven't even read what the question's asking, but we're starting with our balanced chemical reaction. That's always going to be step 1. So then it tells us 82.5 grams of carbon dioxide is produced. So we could write over here 82.5 grams produced. That's telling me that this is an actual yield. So anytime it gives us information about here's the amount of product that was produced, that we obtained, that's an actual yield. So if we think about our actual yield and our theoretical yield, the actual is what you get, and the theoretical is theoretically how much could you produce if everything went perfectly, which is very unlikely to happen, right, in the real world, but this is our actual yield. And so that was produced when I reacted 81.10 grams of octane and 389.1 grams of oxygen gas. So at this point, I'm immediately thinking limiting reactant, right? If I've got 2 different amounts of my starting material, then immediately I need to start thinking, well, what's the limiting reactant? So step 2, so let's write that over here, limiting reactant, question mark. And based off of my limiting reactant, then I'm going to be able to figure out my theoretical yield, and then from my theoretical yield and this given actual yield, then I can actually find the percent yield, which is actually what we're looking for in this problem. So that equals the question. So percent yield is equal to the actual yield over the theoretical yield, theoretical times 100. That's going to be my percent yield. So this is the equation, more or less, that I'm going to be using later on down the road. Okay, so now we're ready to actually start the problem. So all of this, right, this is just groundwork. I've spent 4 minutes, just laying the groundwork, organizing my information before I even really get started with the problem. So I would really recommend that, if you're just starting out with these types of problems, you do a really good job of organizing, you lay out everything very clearly before you even really get started with the problem. That was an interesting 8 I just drew there, but anyhow, the first step, I'm going to convert from grams of C8H18, grams of octane, into moles of octane. So that equals 0.710 moles of C8H18. The purpose of this is to figure out what my limiting reactant is. So it's either going to be my octane or my oxygen. But to figure that out, I need to first figure out how many moles of each starting material I have. So then for oxygen, that's 12.16 moles of O2. And then the way that I like to show this limiting reactant is to figure out how many reactions I can do with the given number of moles of my reactants. So this tells me that I could do 0.355 reactions with this number of grams of octane. So let's go through the calculation that I did here for octane. First things first is I converted from grams into moles using my molar mass of C8H18, just calculating what that is. So I got my moles of C8H18 and I got my moles of O2. So these two numbers here, they're very important, right? They're telling you how many moles, what's the number of different atoms or molecules you have. But to figure out what the limiting reactant is, I like to do this other calculation here that says, well, for every one reaction, you're going to use 2 moles of octane. So that's the coefficient here, 2. And I'm going to do the same thing for oxygen. So every one reaction requires 25 moles of O2. So if you do that calculation, you find 0.486 reactions. So this tells us, reactions, that this is our limiting reactant, that octane is actually our limiting reactant in this case because this number is less than this number. This is telling you you can do 0.355 reactions before you run out of octane. This is telling you you can do 0.486 reactions before you run out of oxygen. So clearly this is going to be our limiting reactant. So we have determined that C8H18 is limiting. So that's a good start. And then for the last part, we're going to figure out what our theoretical yield is. And then from that, we can figure out what our percent yield is. So now that I know that this C8H18 is our limiting reactant, I'm going to take this number of moles down here, and I'm going to say 0.710 moles of C8H18, that's going to be our limiting reactant, will be able to form some number of moles of CO2. So I'm going to use that mole-to-mole ratio again, and I know that 16 moles of CO2 will be formed every time I consume 2 moles of C8H18. So my number of moles of CO2 that I'm going to form is going to be 5.68 moles. This is my theoretical yield, right? Theoretical yield of CO2 is going to be 5.68 moles. I can convert that to grams because I've got my actual yield in terms of grams. So just converting this to grams would be 44.01 grams over 1 mole equals 249.9 grams of CO2. I think, oh, no, so I guess for these numbers, we should have 4 sig figs. So I was just checking my sig figs there. These two numbers here both have 4 sig figs, so my answer for my grams of CO2 should have 4 sig figs. So this is my theoretical yield of CO2, and this 82.5, that's my actual yield. So to figure out my percent yield, I'm going to take my actual yield, I'm going to divide that by my theoretical yield and multiply by 100. So let's just move this down here. So the last step, step 4, is going to be percent yield equals my actual 82.5 grams divided by my theoretical 249.9 grams times 100 equals 33.0%. This number is going to have 3 sig figs because my 82.5 value has 3 sig figs, so my final answer is 33.0%. That's the percent yield for your chemical reaction. So that's telling you when you ran the chemical reaction, basically you got only 33% of the total amount that you actually could have gotten based off of your limiting reactant. But sometimes that's how these chemical reactions go. Sometimes you don't isolate all of the product that you're looking for. So this percent yield here is definitely reasonable. Typically, in reality, your percent yield will always be below 100. You should never have a percent yield that's higher than 100 because then you're creating matter out of nothing, which you can't do. So when you're thinking about your percent yield, you're always going to want to have sort of the smaller number on top. It's an easy way to remember that. But actual over theoretical times 100, that's the calculation that we should do. All right, so I hope that helps. Like you can see, there's a lot that's going into this one problem. It's 1% yield problem, but I've got multiple steps, multiple other problems. I've got balancing chemical reaction topics. I've got limiting reactant topics. I've got theoretical yield topics, and then finally my percent yield at the very end. So hope that makes sense. Let me know if you've got any questions. Cheers.